Hi everyone, welcome back. So now let's talk about how we would actually apply straightness to a hole. We did a cylinder last time, let's talk about a hole. So we want to control that drive median line, and yes, holes have one too. It's just the center of the hole at all points. Now it's different how you apply this depending on if you're in a model or in an orthographic view. In an orthographic view, you get this extra ability where you can say, okay, I can have my dimension over here, and I have my tolerance on the other side, just kind of sandwiching it. However, for models, you only have one method, which you also see in an orthographic view, which is you have your diameter dimension, and then underneath that directly, you will have your straightness tolerance. So orthographic view, you get this. Model, you only get this one option. Now, one thing to remember is that if you're applying it to an axis, you've got to include that diameter right there. That's what's going to control the drive median line. Okay, last time we went over the virtual condition of a cylinder. How about the virtual condition of a hole? What's that virtual condition for a hole? Well, for a hole, it's the exact opposite. So last time we had the max virtual condition, and we added the tolerance. This time, the max virtual condition, which is the smallest hole, minus the tolerance. Last time we were saying, like, it's like a big, if we were to make a hole that was that exact size for a virtual condition, and our part could fit through it, well then at least its straightness tolerance is passed, as long as its size tolerance hasn't failed. So it is the opposite, okay? For a hole, you subtract off the tolerance. You're thinking of the smallest hole possible that would, have our part still not break that line. Because we can have a perfect cylinder and it can go down to 0.75 minus 0.006. So a cylinder with a diameter of 0.744 at all points is at the max virtual condition. Then beyond that, it's got this variation that's allowed of 0.005. So it can vary back and forth by 0.005. So we're at 0.744. If I vary inward 0.005, well, that's going to be 0.739. That's the virtual condition. It can't break that boundary. If it does, it fails. But if we had this max virtual condition modifier, then as we move away from that boundary, we get bonus tolerance up until we start breaking our size tolerance. We can't break the least material condition. So this bonus tolerance is amazing because it's a way you can increase the tolerance on parts and actually have more tolerance and have parts pass when they would have failed while still meeting the function. And it makes sense because if you have a hole, usually you're going to have some sort of screw to go through that hole. And so the larger it is, the more angled that screw can be, or the less straight this hole could be, and the screw still make it through because it will still have an ability to get through the hole, even if it is very varied. And here, it still has that tolerance zone, that virtual condition that can get through. So as long as my screw, or I guess a bolt, is less than my virtual condition in diameter, it will always pass, even as my straightness tolerance changes with the size of my hole changing. Because that virtual condition does not change. It stays the same size, no matter what my tolerance zone is. Sorry, what my level tolerance is. Now, how do we verify the drive median line straightness? I'm just going to say this, coordinate measuring machines. We can also do functional gauges, which are pretty awesome. Like I was saying before, I could have a hole that is the virtual condition of my cylinder, and I could see if a cylinder could pass through. If it can, it passes. I could also have a cylinder, which is the virtual condition of my hole, and I could see if it can pass through the hole. And if it can, great. If it can't, it fails. Computer-assisted methods are probably going to be the most reliable, though. So I would suggest you use them. We have plenty of machines, like these coordinate measurement machines are amazing. It's where you're going to tap various points on the surface, and then it will know exactly the size and location of all the features, and then with that you can determine if it's passed or not. So in this class, I'm not going to make you actually measure these things, though occasionally I will give you pictures like this, and I will ask you if something passed or failed. So be used to this. In this case, right here, you can see that the variation is never more than 0.003 at any particular point. Now right here though, it has varied more than that. There's variations of 0.005 at some points, and that would mean that it had failed. Okay, now let's look at those gauges again so you can see what I was talking about and drawing terribly before. So a gauge is a part you might make that has a very, very, very fine tolerance. I mean, it's made as perfect as you can make it. And the thing is, you only want to do it once because you're going to check a bunch of workpieces. You only ever make a gauge if you're going to be testing something 1,000 or 10,000 times, and you want to do it quickly and accurately. So it's only good if you just need to check a bunch of pieces. Otherwise, you're wasting your time and money to do this. Now, for a cylinder, the virtual condition is my max virtual condition, which is the biggest cylinder possible, plus this tolerance. So it comes up to be 1.015. And if my piece fits through, then it passed that straightness tolerance. It worked. Now, it still has to have the right size tolerance, so if it was too small, then it would fail in that regard. If it passed its size tolerances, then if it can fit through there, it would pass its straightness tolerance. For a hole, the virtual condition is the minimum size of that hole, because that's the most material, be the smallest hole, so 1.000 minus 0.01, so that's going to be 0.99, and I would also subtract off my tolerance, minus 0.005, so 0.985. And I would have a gauge, which is a cylinder, which has extremely fine tolerances. That's a completely different course, but extremely fine tolerances. And if it can fit through your workpiece, then your workpiece has the proper straightness tolerance, so long as it didn't fail in the size category. Okay, now these functional gauges only work if we have that max material condition modifier. It's not good with the RFS straightness tolerance. In that case, you're going to have to use a coordinate measuring machine, or if you're going to do it by hand, you have to do individual readings taken on both sides of a part to figure out where the derived median line is. So functional gauges, only for that max material condition straightness tolerance. Otherwise, you're going to have a very bad time. So thank you for listening, and I'll see you all next time. Bye-bye.